Hello students, have you ever wondered why do people say that when you are sitting in a car and lightning strikes, why you are safe? Or in a similar manner, if any kind of lightning strikes, it's asked for you to be sitting on a table or something like that. Why are you asked for that? The reason is that that car acts as an equipotential surface, because when lightning strikes, all the charge is going to be completely distributed on the surface of the car, and unless there are pores in it, the charge is not going to get inside the car, and therefore within the car you will not be feeling any kind of influence. So let's try and learn more about this particular part, that is equipotential surface.
What basically is an equipotential surface? The surface at every point of which the electric potential remains same is what is known as an equipotential surface. Okay, so this is how we define an equipotential surface. So if we talk about this particular surface, so here this is an equipotential surface. The reason being, all the electric field lines are pointing outwards, and they have the same value because they are at the same distance from the center. Right, so that is what is an equipotential surface. So any surface like this, for instance, here it's an equipotential surface, here's a spherical equipotential surface, here's a kind of hyperbolic equipotential surface, and so on. So dashed lines are the equipotential surfaces that we have. So what basically does an equipotential surface actually stand for? The name equipotential surface, when we have to define, is given to any kind of surface which consists of a continuous distribution of points. It's not that at a particular point you have a discrete distribution, at another point you have discrete distribution. It should be continuously varying. If there is no continuous distribution, if there is a discrete one, there is going to be a potential difference that's going to be produced. That is not possible. For an equipotential surface, it should be continuous. Yeah, and moving on, equipotential surfaces are always going to be perpendicular to the electric field lines. So for instance, here this is an equipotential surface, this is an equipotential surface, and so on. So these surfaces are always going to be perpendicular to the electric field lines, and no work is going to be done by the electric field on the charged particle while they are moving on this particular equipotential surface. So if you have any particular charged particle that's moving on this equipotential surface, no work is going to be done, because all the points are at the same potential. How can you do any work? There is no difference in electric field, so there is no work being done. You can give a kind of analogy to the gravity. So the equipotential surface is nothing but like the height lines on a topographic map. You would have seen kind of lines drawn with the same topography or the same height with the same color. In a similar manner, all lines with the same temperature are drawn with the same color. That is a kind of equipotential surface as well. So from these surfaces you can find out the same height, or similarly whether you're going up or they're going down in a similar manner. So if it's at a lower height, the equipotential surface is going to be wider. If it's at a higher height, the equipotential surface is going to be slower for the case of gravity. Okay, so let's try to understand this more properties. So properties of the equipotential surface: there's no work that's going to be done while you're moving a test charge over equipotential surface. In a similar manner, the electric field is always going to be right angles to the equipotential surface. What I mean by that? So for instance, here the electric field lines is going to be going like this, this, and this. So at this point, it's always going to be perpendicular. It's always going to be perpendicular to the equipotential surface. The equipotential surfaces are going to help distinguish regions of strong fields from those of weak fields, right? The equipotential surfaces tell you the direction of the electric field, because the direction is always going to be perpendicular to the equipotential surface. If you know what's an equipotential surface, just draw a perpendicular to it. That's going to be telling you about the direction. Further, this is the most important point, that no two equipotential surfaces can intersect each other. If you have two equipotential surfaces intersecting each other, that means there are going to be two directions of the potential. So there can be a possible value of potential difference, which cannot be possible at all at an equipotential surface. So this has to be always kept in mind, right? Okay, now let's understand about a numerical. So what we have here show that the normal component of the electrostatic field has a discontinuity from one side of a charged sphere to another, given by E2 minus n E1 dot n equals to this. Hence show that just outside the conductor the electric field is given by this. What is n? N is nothing but a unit vector that you know. What is sigma? Sigma is a surface charge density. So when we are trying to find out the electric field due to the other surface of the charged body, the electric field expression is going to be given by something like minus sigma over 2 epsilon naught into n cap. This you can find out. So the electric field is going to be given by this particular expression. Now moving on to the next page, let's try to understand it further. So what we have, we know that the electric field on due to the other surface is going to be given by this that we just saw, sigma over 2 epsilon naught into n cap. Epsilon naught is nothing but the permittivity that we already know. Therefore, what is going to be the difference? The difference, because there are two surfaces, so E2 minus E1 it is. So this particular difference, what is going to be this? So this is going to be just added up, because one is going to be plus, other is going to be minus. So you will get sigma over 2 epsilon naught n cap plus sigma over 2 epsilon naught n cap. Therefore, this comes out to be sigma upon epsilon naught with n cap. Therefore, what does this mean? So, if you multiply, because n you know is a unit vector, so product of unit vectors is just 1. Therefore, if I just say E2 minus E1 with these are vector components dot n cap, so this is going to be just sigma upon epsilon naught. Why? Because n cap dot n cap is what you are going to get. That is nothing but 1. So you'll get sigma upon epsilon naught. But inside a closed sphere, you know that E1 value is going to be 0, right? So if you say that this is what it is, therefore the change in the electric field or the difference in the electric field is nothing but E2. So in that case, you'll get simply minus sigma over twice epsilon naught with the n cap. The electric field just outside it is going to be given by this, and inside it is going to be this expression, right? Hopefully you followed till this point. Stay tuned for more.
We learned about what are the equipotential surfaces. You have a conductor in the form of a sphere, then you have equipotential surface which are spherical in shape. You have a conductor in the form of a rectangle, then equipotential surfaces are going to be plane surface parallel to the surface of the conductor. So on these equipotential surfaces, there is no work being done, because effectively you are at the same potential. So you are not going to be doing any work when you are moving in the same potential surface. Therefore, on an equipotential surface, there is no electric field. So this is a very, very important point. Now we move on to the next part, understanding how do the equipotential surfaces also influence and in finding out what is the potential energy.